So we're just looking at some homework questions and student hours. And so I thought I'd record this for those who weren't here and maybe want to see some more examples. But this says determine the points at which the given function f of x is continuous. We're given that f of x is equal to the absolute value of 3x minus 1 plus 6 sine of 4x. In this example, we want to look at our domain and see if we have any trouble spots and if we have to exclude anything. And looking at this, I don't have any values underneath the radical. I don't have any values which are in the denominator. And so it looks like I'm okay. And this trig function, sine is continuous everywhere. It's defined for all real numbers. And so looking at this, I see that there's no problems. And so it's going to be continuous everywhere. And so this one really should just be negative infinity to infinity. Because I know this 4 times the x, that just, remember, 4 times the number, that just shrunk or extended what the period, how fast it repeated itself. And that 6 in front, all that did to the sign is that made it so that our amplitude was 6. So that doesn't affect anything of it being continuous or not. And if we look at a function, the absolute value of a function, it's just a V shape. And so that's continuous everywhere. So the sum of two continuous functions also has to be continuous everywhere. And so that one should be negative infinity to infinity. Then the next problem is very similar. This one, at what points or point is the function y equals f of x minus 2 to 1/3 continuous? So describe the set of x values where the function is continuous and use interval notation. And so again, I look to see, do I have any trouble spots? And so if we rewrite this, it might help you to rewrite this. So instead of rewriting this as a rational exponent, let's rewrite that as a radical. And so if we looked at this, this is really the same thing as y is equal to the cubed root of 4x minus 2. And so since I'm taking an even or odd index, that means I can have negative numbers underneath that radical, and I would get back a real number. And so there's no values that I have to exclude for x in this case. And so I know that this is continuous everywhere. And so it's continuous from negative infinity to infinity.
So only if the radical was an even number, that's the only time you have to go greater than or equal to 0 or whatever.
Exactly.
Okay, that makes sense.
That makes a lot more sense because that's what I was getting confused about, because I noticed the example you used in the lecture was using a even, like a fourth root. So that's where I was getting a little confused.
Yeah, and so that's where we have to be careful. So if our index is even, and like Sean just mentioned, that's where we have to take what's underneath our radical and set it greater than or equal to 0. Unless it's in the denominator, we strictly set it greater than 0. Can't have a 0 in the denominator. And so we just kind of take our functions, we break them down into pieces and look at, see if each piece, if we have a sum or multiplication, are those pieces continuous? And then we can use those rules on continuity to say, okay, if I have a function that's continuous times a function that's continuous, the rule of continuity says that multiple also has to be continuous. Okay, so the next example says determine the limit as x approaches the given x coordinate and the continuity of the function at that x coordinate. Okay, so we're looking at the limit as x is approaching 5 pi over 14 cosine of, so we have a composition of function. Inside we have 7x minus cosine of 7x. And so I know 7x is continuous, the inner function, and I know that minus cosine of 7x is also continuous everywhere. Cosine is a continuous function everywhere, and so I can use my rules of limits to bring this limit inside. And so we can say, well, this thing here is the same as saying cosine of the limit as x approaches 5 pi over 14 of 7x minus, and let's look at the limit as x approaches 5 pi over 14 of cosine of 7x. So if we just did direct substitution, we have cosine of, well, plugging in 5 pi over 14 wherever we see an x there. Notice our 7 in our numerator is going to reduce with our denominator. So 7 goes into 14 twice. So we can rewrite this as 5 pi over 2. Oops. Yep. Minus, and so now we're going to look at the limit as x approaches 5 pi 14ths of this piece. So this is cosine. Again, 7 times 5 pi 14th, 7 goes into the denominator. So this is really cosine of 5 pi halves. Let's look at 5 pi halves for a second. Well, 2 goes into 5 2 times. So this is the same thing as 2 pi plus, and we're going to have 1 pi halves left. Pi halves. So I know that if I'm thinking about my unit circle, I've done 1 full rotation, right? Plus a pi halves. So this is going to get me up to 5 pi halves. I'm also thinking about my cosine of 5 pi halves. Well, cosine of pi halves, which is the same thing as cosine of 5 pi halves, that's 0. So I have cosine of 5 pi halves minus 0. So again, cosine of 5 pi halves is 0. So we should get back that that limit is 0.